This is the Convergent Science Network podcast.
All right, we're running.
Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
This is Paul Verschure for the Convergent Science Network podcast, together with my colleague Tony Prescott, and we're here at our BCBT Summer School of 2015 with Ranulfo Romo. Ranulfo, you came here from Mexico to share with us your incredible work and also this long tradition of work that you've been engaged in on understanding decision making in the brain. So, what's so special about decision making?
I think decision making is the crown of brain function, because sooner or later you have to make a decision, whether it's conscious or whether it's unconscious. Habits, I think, for example, require decision making. They probably are below our conscious. When I walk in some way, I have an apparatus in my spinal cord, together in concert with my brain, allows me to move. I don't have to be very conscious, but from time to time, I'm conscious of where I'm going, in what direction, where my steps are, etc., etc. So, but there are decisions. I think we are talking about decision making in the way in which we can think about. For example, if my girlfriend asks me to marry, I can reflexively say yes. I can say, listen, why don't we talk in a week? Or, for example, in a month, I have a friend that have delayed that decision for 8 years.
Okay. But now you have actually looked at this problem of decision making with respect to marriage in a much more compressed way, in a much more controlled way. You reduce it down to somatosensory decision making, right? Where you really have to, let's say, combine signals from different modalities and sort of extract a meaning from them relative to your goals and then act accordingly. Okay, so why did you choose somatosensory decision making?
For various reasons. The first one is because I was trained in a very long tradition, coming from Philip Barr at Johns Hopkins and in the 1920s of the past century, and then continued by Vernon Mountcastle. And third, because, believe me or not, but the reward signals were discovered using somatosensory signals in Freiburg with Wolfram Schulz. And then, trying to think about, I discovered that behind this, there was a fundamental problem, at least for me at that time when I was young, with Vernon Mountcastle, the representational problem. One question is how the brain cells represent sensory inputs, no matter what is the sensory modality. Somehow, you have to generate a neural copy of the external world. You don't feel with your fingertips, you don't see with your eyes, you don't hear with your ear. You do all these sensory functions with your brain. And the question is, well, how does the brain manage to generate a representation of the external world? Just to begin, as a prelude to decision-making, perceptual decision-making. So then, the question is, once you start to generate sensory representations, you are training your network. In such a way, you generate experience. And when you generate that, you treat sensory inputs in a different way as if you were a naive organism. Once you have that, you have to think about what is experience, which is memory, whatever you label it, whether long-term or short-term memory. So the question is, how do we store sensory input information in our brain that makes what we are? So that's one of my general questions. So at the end, we want to understand how these big problems sensory representations and internal representation combine together to generate perceptual decision making. But you can have only perception decisions alone with little experience if you were a very low organism animal, or you can make, in your case, you use your internal experience in order to make decisions. You don't need sensory input sometimes.
Mm-hmm. But now when I might move my eyes, right, to have a differential response to stimuli in the world, I might push a button, or I might decide to get married 8 years from now. So these are all forms of decision. So do you think that decisions in that sense are hierarchically structured, or are they really situated at a specific level in, let's say, a hierarchy of perceptual cognitive operations?
If you are an eclectic man, you have to think that happens all around this. It can be an hierarchical processing, different situation. And I think what is important in our brain functioning is that we depend a lot on context. So our brain adapts to the context every time, context situations in such a way that one decision at this moment can be, even if it's exactly the same operation in another context, is what's going on. We are context dependent. We are no more than that, I think.
But then, so if we put it so broadly, so now it's decision making is very much helping us to transform, let's say, sensory states into an action in the service of our goals. So what we have to bring together is sensory states, our motivations and goals, and our action repertoire in the end to produce this one output that will drive our skeletal muscle system. And given that we only have one skeletal muscle system, it better be one action. Okay. So there's this funnel we have to go through to get sensory states into action. And this funnel is modulated by different things, goals, memory, action.
Yes.
Right? But now at the beginning of this funnel stands the sensory process. And there, what I found interesting, in some sense, you take a very extreme perspective, in my opinion, on sensory processing as really insisting that a primary sensory area is really primary in the sense that it is uniquely dedicated to the modality that the thalamus dictates to it. So you really believe that to be the case?
I do believe. And it's not that I believe. I think, because it depends on hypothesis and results and interpretation and challenging that hypothesis. In fact, I cannot say that I have lost more than 10 years doing experiments in order to not to convince myself, because no matter what is the result, is fine to me. For example, in one extreme, many colleagues say that early sensory cortices, the earliest stage of processing in our cerebral cortex, is multimodal. In the other extreme, which is almost a dogma, is that early sensory cortex are unimodal. They have only one capacity to process only one modality. Just, let's say, visual cortex is visual cortex because it does receive an input coming from the retina, going through the thalamus, and the thalamus dictates that territory to be visual. And for the auditory cortex, exactly the same, and for the somatosensory. But there, in science, it's very important to insist and to challenge dogma, even if we lose time, in the sense that we lose money, we invest many hours in something that does not produce something positive, a positive result. It might be a negative one, but it's very important in order to allow hypothesis or interpretation or something, a fact, that is true or not true. So, in fact, over the last 10 years, I've been insisting and trying to document whether unimodal, whether multimodal. At the moment, it wins unimodal.
So what was the key piece of data that convinced you that it was unimodal?
I'm relying in a very simple signal that I think come from the Cajal tradition, the neural doctrine, in the sense that neurons, that the brain is made of pieces of individual neurons that are connected together by a tiny space called synapses, and that all the territories of our brain, at least for the sensory and perceptual territories, are dictated by our sensory lamina. Let's say, for example, somatosensory cortex is somatosensory because it's connected to our receptors in our skin, our body, in such a way that our brain makes a map of our body surface. And in the visual cortex is visual because it's very related to the retina in such a way that the retina can be mapped out in that part of the cerebral cortex. And the same for the auditory cortex. So, in the beginning, in the mid-19th century, there was a big effort by physicists in Germany, Helmholtz, something that started to set out the basis of the action potential, that there was a transmission of signal from the skin up to the brain. And they were able, in the beginning of the 1920s or something like that, the English school, to discover the basis of the transmission, that the signal that uses our brain is signals. And Cajal had already settled out the neural doctrine. So I'm using a very tiny signal from this old tradition in order to map out the responsive properties of brain cells. Not only responsive properties, but once the stimulus is gone, something our brain is working at this moment, and in fact I'm talking about is internally generated by my brain.
You're looking at the S1 cortex particularly, and there are other somatosensory areas. Have you looked into those too to see whether there would be multimodal cells there? Because there are other projections, certainly I would know in the rat, where the sensory input comes in from the periphery, but may mix in primarily sensory areas, perhaps more cross-modally.
It was clear to me for about 30 years when I was working with Wolfram Schulz, a very dear colleague, that in order to understand the function in our brain, we have to go across cortical areas. So when I started to work out in Mexico City, I decided to use exactly the same input and see the transformation across the system, which is something very important. It's like, for example, if I tell you something, you interpret it, and then you tell something to Paul, not in front of me, and then Paul tells to some others, something like that. It's like I'm passing to you directly the information, and then you treat this information in a different way and pass that information to Paul. But Paul never spoke to me. So it's more or less what's going on in the brain. It's a metaphor that is like, in Spanish, who says chismoso. It's not liar, but what Paul interprets from me is through you. It's what I'm trying to do myself across the brain, trying to understand what kind of representation receives a very downstream area outside the sensory representation, for example, something like that. So I think that's the major contribution of my work, going in this direction, in which it tries to see what's going on across the brain. Because I think, at the end, what Paul says is the true representation for Paul, and what you say, your true representation, and not necessarily exactly the same, and share with myself too.
And I understand you're trying to do a very pure experiment. You're going to try to simplify it as much as you can to get at this basic process of decision making. But the criticism that I guess people can make, and you already responded in your lecture, is that this isn't what happens in daily life. So much of the time the stimuli coming from multimodalities are telling us similar information, and pays greatly to pay attention to them together. And also, even in the touch system, which you're describing, most of the time we are actively controlling the way that, for instance, the fingertip is moving on a surface, and that's going to have a huge impact on how we process that signal upstream. So when you're in your experiment, you essentially stimulate the fingertip as a passive receptor surface. Perhaps you're missing something about what was more common for that sensory system to be doing, which is to be actively controlled in finding useful information. So the information is being given here. There's no sense that I have to look it out.
Well, you're right and you're not right, as always. First, yes, I'm dealing with basically with the touch system and use it as a model of processing. Because the general question is how a sensory representation, unimodal as you like, is transformed up to pole or something like that, and produce a function, which is a very complex issue. The second issue is, and you raise, which is very good, is that is a criticism, is very welcome, is a passively delivered stimulus. And normally, for example, I am squeezing my fingers across the surface in order to get information. But that's the way science works. We would like to have an experiment in natural condition, but this is almost impossible because it's very difficult to control our variables, and you can dribble wrongly in some direction because there are many cues, many things that must take you in a very different direction. And myself, I had decided to control as much as I can where I deliver the stimulus. Exactly the same as the people work in the visual system. What people in the visual system do is very simple. Normally, we are moving the eyes, but we have to bring the fovea in a given moment to deliver the stimulus. Otherwise, it can be in different ways, and make sense of sensory processing, visual processing will be very difficult. So that is a decision that I made because I made it. Of course, I can be wrong, but it provided some pieces of evidence. Of course, it's not telling to you how the sensory motor loop works. I do not pretend it. I do not pretend even to show intentionality from the active point of view, because if I want by wish, which I do not know what is a wish, for example, my desire to do something, from where does it come? I do not know. But eventually, if you know, you can move your hand, you can move your finger, you can walk, you can think about or something like that, and then use your senses actively. So in my case, I do not pretend to do. I can to do in the opposite way. Just simply want to see in a very, in Spanish, which is castiza way, how a sensory input is represented by brain cells, and bring a big network of our brain to thinking and deciding and using, if you like, the motor apparatus afterward. In other words, I'm very interested to know what is behind a decision report.
So now let's say we convince Tony, okay, and the sensory stimulus is sort of ecologically valid, and even we can discuss details of that later. Then the real decision making doesn't take place at that stage. The real decision making takes place in areas that are sort of in frontal areas of the neocortex. So what kind of network now gets engaged? So here I have my two stimuli. They might be frequency modulated in some way. My primary visual somatosensory areas are responding. They're now transducing this stimulus to a prefrontal network that's going to make the decision. So what's happening there? What's going to happen?
This is a very important question, because at the end, thinking early in the morning when I am alone in the dark, my dark room, or eye closed, And the other day I was thinking about what is the point of this? Of course, I many years ago discovered that I was not a somatosensory man. As the people say, I'm a visual man. I'm not visual. I'm using a model to understand something. So at the end, if I can simplify my thinking about this. For example, your organism, we and animals, even the lowest animal, you need to map out something which is happening in the external world, transform energies in something. And the current money to transmit something is the action potential, electrical signals. But there had to be receptive areas, even if in the lower levels, that very quickly take these signals and then do a response. Those are very fast systems. Even the sensory ones that go up to the cerebral cortex in our cells. So that takes 25 milliseconds in the somatosensory system. And if you think about the spinal cord, is 10 milliseconds. That's exactly what's happening in a world. But fast, and then fast responses from the motor side. You have to do, but in our cases, it can be, you can treat these signals and store it in some way. Those are slow systems, the working memory ones, for example, that allow you to think about. And so those are very slow systems that depend on some other kind of transmissions, molecules, differently to the ones associated to sensory and motor output systems. And there are the dopamine system, cholinergic, noradrenergic, serotonergic, or something like that. Not special cells, but are localized in such a way that can add something to this fast transmission and more or less slow transmission. So at the end, you have a trio there. Fast sensory input, fast motor output, and something in between. And you can put many things: memory, motivation, decision-making, subjectivity, and something like that. And when something is a mess out of this, then you have frustration, you have psychiatric problems, memory problems, etc., etc. But I can put in troubles. If I cut the sensory input, the rest doesn't work. If I cut the motor output, too. So there is something in between, extremely important, and that's the one I want to understand myself.
But now, do you see this as one monolithic system that always converges onto then the same decision, evaluating the same information, or do you see this as competing subsystems?
Absolutely. I think, for example, if I were a Martian, if I go and see Paul lying in the bed, if I were a neurologist, I would say it's a motor problem. But eventually, you are in depression. You don't want to move. I call you, Paul, good morning, and you don't move. And I can say, well, it's a sensory deficit. Mm-hmm. Or secondly, you don't move, it's a motor deficit. But simple, you are out. You don't want to hear, you don't want to move. Mm-hmm. Those are the systems who are in troubles in between. A Parkinsonian person, for example, I'm sorry if I use this, but if Miss Universe crosses in the field, it doesn't move. It doesn't care. Something, because it doesn't care. Probably the sensory input is there, but there is no more motivation. There is nothing. It's an empty brain.
Mm-hmm. So now we have the decision-making system, or however we want to call it, because maybe this is now more than just a decision-making system, right? We have a perceptual system with the motor system, and there's the something in between. We're going to call that the decision-making system, or we're going to give it a different name?
No, I think it's just whatever you do in life is always decision-making. Mm-hmm. But decision-making needs to be expressed through a voluntary action. It's not a reflex. So, for example, you do not move. You can think about. You can even, we have a paper called postpone decision. For example, when you go to a bar or restaurant and the waiter come to you, give the menu, and you say, I don't know whether to take this or that. Then comes the waiter in a minute, say, have you decided? Oh, give me a minute, normally we say. And then finally you are under pressure and come the waiter, have you decided? And you decide. And then when the waiter goes, you say, why did I decide this? So decision-making is something like that. When you are allowed to make a postponed decision, which is always I do myself, and it's called procrastination, which is a true mental problem that I have myself. For example, I do receive an email, and I know what is my decision, but I postpone it for, I will do it tomorrow. And when tomorrow comes, I say, I will do it tomorrow. And at the end, I say to myself, what's going on with me? I have to make a decision. My decision was made before. I don't know what that. There is a colleague in Israel which is doing a modeling about this. It's a fantastic work. And I think there are some mental diseases which are not taken by certain in the society, but I have that problem myself, is procrastination. No doubt that.
Right.
And as we do have many memory problems, which are perfectly adaptable to what people can think is normal, but it's not normal if you make a simple test.
Right. So, well, I'm quite a specialist myself in procrastination. So you're not alone. I can assure you. But now, so okay, we have the sensory signals. They are sort of. We have strongly stimulus-locked responses in our sensory areas. They converge over a number of steps into a premotor area like PMC. You pointed to a number of areas.
Yes.
So, is this information reaching that area simultaneously? Is there any kind of coordination across these signals? Like, say, primary somatosensory area is just in distance closer to frontal areas, PMC, as might be a visual signal. So do these areas care at all about latency matching of these areas that project to them?
Of course. For example, the sensory input, which you can quantify in the stimulus parameters there, takes about 25 milliseconds, the beginning. You can have a very faithful representation of, at least for this stimulus. When you go to the frontal lobe areas that treat the stimulus in a different way, but you can directly decode the information there. It's about 180 milliseconds. So there is a delay time between that sensory representation and what you see there. Of course, if you fill the gap between the two, you can find out some areas 60 milliseconds, 100 milliseconds, something, which is a time. And I don't know why. Why is not directly, for example, from the skin to the MPC to the frontal lobe? It needs to be treated. And that reminds me Benjamin Libet, who was very much engaged in trying to understand the time it takes to make conscious something, a sensory input, for example. He always referred about 500 milliseconds in men. But his techniques were not perfect at the time. It probably is about 200 milliseconds. No matter what is the sensory input, I have spoken with people working in the auditory system, in decision-making, in the visual system, somatosensory system in my case. It takes about a signal which is consistent with the period in which you make the decision, which is about 180, 200 milliseconds.
But that's, in Libet's case, he's talking about the conscious awareness of the decision. So do you believe that for the monkey, it's a comparable kind of process?
there might be some differences in the timing.
Sure, but qualitatively, it would play out in the same way that we would have.
I do think so.
Okay.
Yes.
Right.
Of course.
So now we have. So in your opinion, the decision making we're talking about, just to sort of finish up the Libet aspect, also decision making is always engaging conscious awareness.
Not necessarily.
Okay.
For example, when you drive your car, you might be aware once you make the decision. But in other cases, if you give me time, which not always possible, because it depends. It's a very adaptable operation. It depends of the time constraints and what beneficial is to make a decision, whether you need to think about or whether you have to make a decision.
Right.
Not in a very reflexive way, because you have brain circuits that allows you to think about below your conscious awareness. Sometimes you are conscious on that, and then you say, why did I do that? Oh, I did quite well.
So your experiment is a little bit unusual in that respect, because you have something which is highly practiced, but at the same time is always intrinsically unpredictable, because you don't know what the next stimulus is going to be, but you know it's going to be one of two things. So now you have something there, I guess you would say you cannot use a habit system, because you always have to make a choice.
Yes.
And therefore it would come into consciousness.
It was made by purpose from the beginning. I thought a lot about this because I was trained by a very incredible man, Vernon Mountcastle, who laid down many of the ideas we use right now, believe me or not. And when I was working with him, in some way we treated this problem, and I discovered that he was doing, at least from my perspective, in a wrong way. Of course, I thought about him, had more flexibility. Because he was older than me, I was eager. So everything was left. And then when I went back to Mexico, I say, why didn't it work? And I discovered why. So I made my purpose, in which in a very artificial way, I could recreate the different steps, one without being contaminated by the next one, but being sure that to pass from 1 to 2, you have to go through this step. Otherwise, you will be wrong at the end. We're simply guessing. So it's very, if you like, it's artificial, but everything is artificial, even CERN in Geneva, in order to prove the molecule, God molecule. So it's made by purpose. But I had to make clear that you had to have both inputs, a central input, an output, and then be combined. And I had to be able to look at both, not in a very different way, just simple, had to capacity with a very simple statistical the technique coming from engineering and physics, just to decode and have them both in my hands. So it's a very peculiar way of doing science, a very simple way. Is pedestrian, frankly.
But now, so what you found is that neurons in MPC, if you looked at how these neurons respond to the task properties. So now, in this case, we have these frequency modulated visual or tactile stimulation, and now dependent on the frequency and the difference, like before the waiting period and after the waiting period, the monkey has to choose for one action or the other. So what you show, however, is in this waiting period of up to 3 seconds, something very peculiar happens, and that it looks like the response of these neurons sort of also at the offset of the first stimulus pair, they slowly ramp up their activity, or actually it might vary, but still reflecting the key feature that should inform this decision, which is frequency. Okay. So But why would that be a ramping activity? Why don't you just latch on to a certain representation of that frequency and just keep it there? What's the ramping all about?
Let me say something that somebody today asked me about. He was posing to me a philosophical question. I admire Democritus, but recently I discovered Epicurus. Epicurus precedes Democritus in the ideas that there has to be a representation of something in the brain. Democritus was talking about molecules, atoms, that everything in our external world was made by atoms that entered through our eyes, our ear, our fingers, and these atoms move up to the brain. He said that, and in the brain, these molecules gather together and give an iso. In the case of the form, an object, they generate the form, and that representation was important for learning, memory, voluntary action, and decision making. Democritus said that 200 and 300 years ago, 2,300 years ago. So, if you like, I'm a continuator of Democritus. So, if you like, the atoms are the action potential right now in the modern view. And those action potentials are how cells generate electrical signals, tiny electric. If you put together, you can generate the form as an image. In fact, Otto Kreufel used this idea to study the form of visual inputs in the visual cortex in the cat. Myself, I'm using a more simple stimulus, vibration in the fingers, and you can see it's not the isomorphic, this is isometric representation. So I wanted to have something that I can see directly from the spikes. And the idea is, to me, the acid test was what is left when the stimulus is gone.
Right.
And I wanted to find out that. And with very simple statistical methods, we see that the stimulus parameter is there. Of course, neurons are like humans, have different ways of represent, but at the end it's exactly the same neural code, a parametric code in different times. And I want to believe that neurons, thousands of neurons, millions of neurons, gather efforts in order to represent something. And this is what is shown.
Sorry, so what is Epicurus that's different from Democritus?
No, it's the way, Epicurus added something. Democritus was more from the physical side, like a rationalistic person would think right now. As, for example, very often the students say, what do you think as this paper? I always say, well, this paper is not very good because very qualitative. And I always tell them, listen, if somebody is able to show qualitative properties of something, it's because he solved everything. Because they always criticize. It's not very quantitative. So what the Epicurus added is precisely the quality. Think, he thought about that. For what for is that? For example, many years when I discovered that isometric representation of the stimulus, I wanted to know whether it served for something, whether it was an artifact. So I did the reverse experiment. I activated artificially brain cells, and what happens that the monkey or the subject had the capacity to generate something which is very consistent with what I observed with the natural stimulus. So there was a very causal confirmation that representation was useful for decision making.
But now we have this slowly ramping activity, and for you the key point here is that what these neurons do is sort of they throw away information that really doesn't matter for the decision making, and they conserve the information that is sort of modality independent and relevant, which in this case is the frequency of the modulation,
yes.
Right? So how does that process play out? Because so here we have we have an auditory and a tactile stimulus. They might have a different kind of frequency response, right? Converging on any of these frontal areas. And now during what you showed, which is interesting, is that during the wait period where the stimulus is gone, the system, these frontal areas that you investigated, are still modulating that signal in some ways. That only this sort of frequency specific response starts to emerge is most pronounced towards the end of the waiting period, just before the decision is made. So how do you see this incremental sharpening of the task relevant information in the response?
This is science. We have no an answer for everything, but it's a fact that happens there. And once you have it, then you can think about. The first thing which strikes me is that this is the way that happens in the brain. Secondly, I'm very impressed that for that cells in a very downstream area, far away from the sensory representation, do that have that neural code in that moment. And so it might tell you something fundamental about that.
Mm-hmm.
So the question is that you are thinking about underrepresentation on a stimulus parameter for different modalities in the same way. It's an abstract, it's a supramodal, a model, if you like, something, but it's there.
Mm-hmm.
What is strike the most to me? So we can think right now in models, in a one stream trying to model and implement model and think about and do experiments in order to find out the biophysical basis and the architecture, neural architecture, which is there. No doubt that is and makes this. To me, the most important contribution of this, I'm trying to think that my work has something worth in life, is that I think we were the first to show in the tactile modality a way our brain cells represent information during working memory. Because in the case of my colleague Goldman Rakish, it was always contaminated by eye movements. And but it's a very the physical space, if we want to think, is there. But in our case, it's something learned. It's something, place cells are there. But the monkeys don't have to think about vibrotactile. Why? Or by acoustic repetition. It's exactly the same. When you study medicine, your brain is not made to do medicine or engineering. You have to be trained. So this is something forged by experience, which means that your brain circuits can be modified by experience, can store information, experience, and can use it for the best or for the worst. That's, to me, the contribution.
But now in your analysis, you looked at these cells as being either unimodal. So we look at PMC, right, the frontal area. You looked at whether these neurons were tuned unimodal or bimodal, right? And then what we see is that over the 3 seconds, initially, actually, they're not that strongly committed to anything. And in the end, we see a very strong, what you call bimodal response. However, would it not be then more appropriate, actually, as you said earlier, to call it amodal?
Yes.
Because what they care about is just that bit, let's say they care about the semantics of the task. The frequency is telling you something important.
Yes.
Forget the rest. Would you be happy with that interpretation?
Absolutely.
Okay, good.
In fact, I spent a lot of time thinking about this. To me, it was the most simple paper in my life to report. But when I started to write, I was confronting literature that there was nothing, or the people used to say they had already discovered. But how to say that? How to confront the community to tell them there is nothing, and how to say I'm a pioneer real in this. So at the end, I have to think about and be very polite and sometimes say supramodal, and sometimes amodal, sometimes bimodal.
Mm-hmm.
But at the end, what happens? We discover very few cells unimodal, and I think it's a statistical issue. And the network is basically more than 85, almost 90% bimodal. And I've been thinking, you don't have to think about the brain doesn't care when once there are circuits that treat the stimulus parameter, but at the end is the goal, is to treat something. What is fundamental here is the frequency. And the cells don't care whether it's acoustic, whether it's tactile, or whether it's visual. I think it's very, very physiological, very natural. This,
But Tony, go ahead.
Are you able to show that these neurons are getting their input directly from the unimodal cells, and they're integrating, or could there be some other site of integration that's perhaps viewed more as a sensory area, so that the integration happens sooner or elsewhere, and you haven't seen that yet?
These cells are very far away from the sensory input, where you see the stimulus parameter. There are many areas in between, and you can see the gradual contribution of these areas. In this, what I show, I simply wanted to contrast input and what you get there. But in between, it's already done the experiments. I can tell you there is a gradual transformation. For example, circuits, neurons from circuits, which are in between this area and the sensory input, that treat the responses during the sensory input in the two ways, opposite way. They share correlated noise, which is shared something common thing, synaptic input, something like that.
Right.
And then populations of neurons which are only in the early components, some others which are more delay, some ones we respond the most during the second one, which is the right moment in which have to combine two different modalities. For example, the first is acoustic, that has to be stored in working memory, and the second is tactile. Somehow, there have to be some gears in your brain that shift gears in a very efficient way in order to treat in the same way to this different sensory input coming for different representation in your brain.
Right.
So that requires tremendous, it's very simple, but to analytically, statistically to prove modeling is another issue.
Mm-hmm. So there's several steps on the path to the premotor cortex. But what about signals coming back? Are there signals from PMC which could be modulating the primary sensory areas?
Yeah, we haven't discovered that, but I was surprised in another experiment in 2005 that that was 2002, that reported in Nature, in which we discovered decision-making in downstream area immediately after S1, primary somatosensory cortex. This is called secondary somatosensory cortex. So everybody would expect that this area is very somatosensory. But we discovered that it was associated to decision-making. They have also working memory cells and combine the working plus the sensory input. So when I got the beginning of the decision-making process, it happens that it was delay with respect to the medial premotor cortex. It's like the frontal lobe send back a copy. Listen, do you agree that I made the right decision? So the beginning of the decision signal was in the MPC, and then secondary somatosensory. I had thought in the opposite way. The secondary, because it was very close to the sensory, had to be the beginner. No. So that showed that there has to be a feedback projection which nobody knows.
Mm-hmm. Okay. But now, so the data on which we base this interpretation is sort of the number of neurons that are responsive in the waiting period to either unimodal or the bimodal aspect of the stimulus. So I guess you revealed that by probe trials, right? That where there's no specific reward to be gotten by the animal, but we just present either the tactile stimulus or the auditory stimulus, and we see which neuron responds or not. How do you exactly how can you tell me, how can we figure out how many neurons are responsive to a certain modality in this time window? Because we have to threshold something somewhere.
Yes. Well, we don't make any assumption, except that we know that this area has the capacity, because we had already shown in the TAC-TAC protocol. So we simply wanted to add whether the acoustic stimulus was treated in the same way, whether those neurons had or not the capacity.
Mm-hmm.
And the second hypothesis was whether we wanted to test whether if that area, the neuron had that capacity, were intermingled, many unimodal or were bimodal. So the only thing we did was to insert the microelectrodes. We insert the wires is there, leave them to recuperate the tissue, because we believe that we perturbate the environment of brain cells. We let the monkey to do the task, that there is no problem. We don't have any statistical bias. We simple, whatever is there, we pick it, and that's it.
Mm-hmm.
The only thing we require is that the neurons are there, that we don't lose the cells across trials, not to have statistical problems. So cells, they have to be stable from the beginning up to the end of the test. And that's it. We don't make any assumptions. So, of course, we would like to have the through populations, but nobody can make it.
Mm-hmm.
Even the people that think that they have massive recordings, EEGs, magnetoencephalographic or fMRI, that's not true. This is the way we are running the experiment in 2015, and there is no more, and we have to rely on that. There will be new techniques in the future which are not available, even calcium signals, because they have to destroy a little bit the brain in very small animals, which sometimes I think they are not doing what the people claim, and they are sampling only some layers, and that's it. So here is what we have, no more than that.
Right. So now a traditional approach or model to think about decision making is what's called drift diffusion in psychology. It has been popular for many years, and now it has been picked up in neuroscience as well. And people are sort of, singing that tune quite loudly nowadays, that everything is about integration of these kinds of simple signals. So now in your model, you show us that the number of cells that now respond to the decision-making variable is increasing over time in a delay period. So I could say, well, isn't that suggestive of a drift diffusion model? Because now I have just another neuron that must read out this whole population. The more neurons respond to the frequency, the higher the rate it will get, and until it reaches its decision threshold, and there we go. Is this how you think about it?
No. In fact, I have followed a very different way myself, thinking in that having hypotheses, having, but in fact, every time we do a statistic, we use a model, But I'm not married with any model. Intuitively, it's very nice, the drifting accumulation model, no doubt that. But it's true and it's not true. It depends how you treat it. And of course, accumulation can be done by the population. And in my case, I show that the signals is more represented, the numerosity increases and the quality too, because it's coming very soon, the right moment in which it's like when you are running the 100 meters, when you are sitting just to listen the ball, the cue signals that trigger the beginning of the 100 meters, your brain comes to a state in such a way that sensory input treated very differently in other situations. Sensory input are not treated in the same way every time. It's exactly the same what happens in this case. It's coming, the second stimulus, and the monkey knows. And in fact, there is a timing signal superimposed on this working memory and the numerosity. And I want to believe that the number of neurons matters in order to do function.
Mm-hmm. So, but still, there must be some thresholding and comparison going on, because all what we look at now is there's the neurons in this premotor network that you measure from are saying, yes, the frequency is there that tells me that we should do A, let's say. I have to move my eyes to the left. So now we have the evidence, but how do we get that then transformed into actually executing that one action?
This is what I like to understand. For example, in fact, what another issue, if I can speculate here, because I'm not doing experiment, I'm simply speaking, is that out of the number of neurons and decoding directly something from brain cells, I would like to understand how subjectivity emerges from the activity of brain cells. Mm-hmm. I frankly have no idea. I know it emerges, but how is the most difficult problem in science. And if we manage once to discover this, that could be probably the most important discovery in science for the rest of the humanity.
Right. I agree with you. So you come out of a tradition, if you want, the giants of neuroscience, right? Vernon Mountcastle, as your mentor. Also, you've been delving into the brain deeply, and also you have very deep thoughts about the brain. So if we want to follow that tradition, what is Ranulfo's law that we should now spray paint on the wall and sort of imprint in our brains every day in order to understand the brain?
I have many mentors. One also could be Wolfram Schultz. In fact, he and I were so young that when we entered into the field, we didn't know, because we didn't know how to study the motor system. We didn't know that we were dealing with reward, which is probably was one of the most important functions of our brain, which is the subjectivity, how treat things. I don't think so that I have a law. I think it's a particular way of treating in doing the way I do science. I'm probably one of the last ones. Is right now science is becoming like industry, and bureaucracy dominates politics or something like that. I do not know whether there will be something left by me, but at the moment, I'm quite happy with what I'm doing. My subjectivity is largely rewarded by the way I do. There might be something which is important. I have dealt with two problems. For example, how the physical world is represented in the brain and track the signals to make decisions, together with working memory or something. And the other one, I want to believe, together with Wolfram Schultz, that we'll deal with something which is very different. It's not a physical parameter. It's something that is generated by brain cells, the reward business. But in spite of that, we were able to decode something. So we're dealing in these two works, the physical representation in brain cells and the subjectivity represented in the brain. And if you like, that could be my contribution. But I have no big hypothesis yet.
Mm-hmm. Okay. So it's like embrace subjectivity. Would that be a good law for Ranulfo? Or at least respect subjectivity?
Of course.
Yes.
Yes.
But now, so the other thing, Tony likes traveling. He wants to go to Mexico City. He's never been there yet. So 5 years from now, he's going to come to your doorstep with a piece of paper that says, look, 5 years ago, you made this prediction, and today I want to know whether you actually have falsified this. Being a Popperian, you would like to have it falsified. So what's the one prediction that you would like to commit to be tested within the coming 5 years?
Well, we are dealing with something fundamental too, and I haven't spoken about it. most of our mental functions depend on attention. And I began doing experiments on this. And it's a big issue. So far, at this moment, there is nobody has been able to describe brain circuits associated to attention. And some colleagues of me think that attention is the key to understand consciousness. So I'm designing new experiments in which I think I will be able to hit on attentional circuits in the way attention matters for working memory, attention matters for perception, for subjectivity or something like that. If you like, I have done the first experiment. If I say my first experiment, I started 3 years ago. So we have gathered enough data, which is part of young people under training. Very young people that I would like they have enough time to continue with this tradition.
Mm-hmm.
So my next thing is to add attention to this.
Mm-hmm. All right. So Tony, remember it, attention. All right, Ranulfo Romo, thank you so much for this conversation.
It's a pleasure.
Thank you.
Thank you.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.
So I made by purpose not to contaminate this the sensory or the treating of this input, the transformation by the motor side.
Yeah.
I do believe that there are motor signals coming back into there because the somatosensory, there is no other sensory system. There is more mixed with the motor out, on the motor side, that somatosensory seems. And we're dealing with the cutaneous modalities. You can deal with the deep modalities. It's a very complex system, the somatosensory.
Well, I think you're also you're simplifying it so that you move the spatial component in terms of where about on the skin that happened, whereas S2 maybe is very
something very important that you were not aware of this. The visual system treats the sensory input with the two eyes. There are two sensory inputs. In this case, it's a tiny patch of the skin. So it's allowed you to trace, clean the input signal, at least at the entry. And then it's very nice because, and then Cajal developed, I do not agree with Gustavo says that the neuron doctrine made a lot of damage. I think you have to take Cajal message up to a certain point.
Mm-hmm.
And no more than that, and stop that, So Cajal spoke about one of his concepts, which is called avalanche in conduction. And he thought about how it's possible that a tiny stimulus in the skin that engages few mechanoreceptors produces a very big perceptual process. And he said that he traced one primary afferent that ends in the skin and then the other branch entering the spinal cord. And he said it's like an avalanche, a ball's avalanche, a small one, a snowball that is moving, is recruiting more and more and more. Something happened like that. The entry of that primary afferent, few primary, recruits neurons in the spinal cord, then recruit more neurons in the thalamus, but preserves somatotropy, and then enters into cerebral cortex and columnar organization, proposed by Vernon and Castle, have divergent. Some other cortical inputs, other hemisphere, downstream structures. So there are many players from a column in S1 that puts in motion everything. There will be a symposium on Mount Castle on November to
really?
Memorial. So I have to think about this.
That's great.
What to say? So I have to talk about models, columns, about distributed systems, somatosensory system, where he laid down some ideas, and what is left from this, and what was not left. I have to be critical.
Yes. Well, I think not much is left by now, right? I mean, it's sort of people
Not
like,
much.
People like these very compressed, simplified models. They really start to forget about the complexity.
Yes, but if you read carefully his chapter in the mindful brain, it had an idea, but he was not beyond that because he was scared that everything was wrong, even with myself, because we designed multiple electro recordings to hit the columns in S1. And very often we had a column and he didn't want to test it. He was scared about that. And of course, I said, why don't we, the monkey's not working very well. I knew quite well that he was confronting something that...
An idea.
Yes. And I asked him, listen, Vernon, why you never didn't go to secondary somatosensory cortex? And reflexively told me, I didn't know how to go. And I said, listen, Vernon, why don't we go at least to the primary motor cortex? No, that's bullshit. The motor system is the worst. And I moved to Mexico in a week, and he did some experiments in M1. And he sent me a phone call to tell me, listen, I wasted time in the primary somatosensory. Now I see neurons associated to decision.
Okay.
So I went back to him to make some collision. We have to make some control, at least to do some recordings of the muscles. So I did some records of the muscles, and those were not decision signals. They were associated to more motor responses. There were missing some controls. And in fact, we published that paper in 1992. That was his last paper in cerebral cortex. But that paper can be criticized for many. So
Ranulfo, I'm going to bring you to the students who want to talk to you about attention.
Please.
Because they believe in